speaker is Amstutz. He will talk about gradient-free parameter approximation for topology optimization and domain partitioning.
Thank you. So first of all, I would like to thank the organizers for this very nice conference. So today I will speak about a few works I have been conducting recently around the perimeter in the context of topology optimization and partitioning. So it's some works I have been doing with these. How did it work? Pointer? Ah, yeah, with these people. So I will not cite them all the time. So once for all. Okay. Here is what you can typically get when you apply some topology optimization method to standard problems. So this is the classical mass problem in 2D for minimal compliance. And during the optimization, as you know, we obtain a lot of bars and more bars, and if you refine your mesh, you get more bars, and usually it does not converge. It converges towards some microstructure, as it has been explained many times during this workshop. So sometimes it can be interesting to find these optimal microstructures, but this is not the thing I will want to do. I'm doing the contrary. I would like to have a domain which is simpler, so without microstructures. And one classical way to do that is to include some control on the perimeter of your domain. So this enables you to control the complexity. So for some to have more some shapes more easy to manufacture. And from the mathematical point of view, you get usually the existence of optimal domains because of this compact embedding from BV into L1. Okay, so this is nice, this is well known, but in practice it's a bit problematic because if you perform shape variations in the sense of Adamar like this, it's okay to consider the perimeter as a penalty or as a constraint. The perimeter has a shape derivative which is the mean curvature of the domain. This is okay, at least from the theoretical point of view. But if you want to do some topology optimization, so for instance, you want to make a hole like this, so you have a domain and you make a hole inside. The problem is that, of course, the perimeter of your domain will increase by the perimeter of the hole, which is obviously of the order of epsilon. So epsilon is the radius of the hole, epsilon power d minus 1, whereas classical objective functionals like the compliance vary like the volume, so epsilon power d. So in some sense you can say that the perimeter has no topological derivative, or said otherwise that if you want to minimize something with the perimeter, you will never create holes. You're always stuck at a local minimizer. So you have a problem from the practical point of view. So an idea is to somehow approximate, replace the perimeter by something with better behavior. So before that, let me recall a few points on the perimeter in the sense I need to do proper mathematics. So this is very classical. So it's the perimeter in the sense of geometric measure theory. So I consider, say, computational box D, and omega is inside D, and what we call the relative perimeter of omega is the total variation of the characteristic function of omega, which can be written like this. And in case omega is smooth, applying the green formula, it's straightforward to check that this corresponds to the classical perimeter of omega inside D, so what we call the relative perimeter. So this is only this part we call the relative perimeter. We don't count this part. And more generally, so we take it as a definition in case omega is not smooth. So we only need that this is finite, and when this is finite, so it means that the characteristic function of omega is in BV, and we say in this case that it is a set of finite perimeter, also called Cacciopoli set. So in this general case, it is well known that so this quantity can be expressed as the Hausdorff measure of this. So Hausdorff of dimension d-1, and what is this? This is called the essential boundary of omega. So it's a part of the topological boundary. So it's a notion of boundary we need. It's related to the notion of density. So in a few words, what it is, you have domain omega, and you take a point, and to know the density, so point x, density of point x inside omega, you take a small infinitesimal ball around x, and you calculate the proportion of in the ball which contains omega. So here density is obviously 1. If I take a point here, so density is 0 because the proportion of the volume inside omega is 0, and if I take here, it's 1/2 if the boundary is smooth. If you have corners, it's something in between. And this is called the density, and so the essential boundary of omega is defined as a set of points where density is strictly between 0 and 1. Okay, so this is perimeter in the sense of geometric measure theory. Now another notion which is also well known is the notion of convergence you need to approximate functional. So in my case it will be the perimeter. So as I said, in practice we can hardly use the perimeter to perform some topology variations. So I would like to approximate, to replace the perimeter by something, by another functional, but I want to do this in order to minimize. So what I want to do is to have, so in a more general framework, I want to minimize the functional f. I approximate by a sequence fn of functional, so on a metric space, and I want basically the minimizers of fn to converge to the minimizers of f. So the notion for that is the Gamma-convergence, which is defined in this way. So we have two inequalities. This lim-inf inequality which has to be fulfilled for every converging sequence towards x, and the other inequality, lim-sup inequality, which has to be fulfilled for one sequence which we call a recovery sequence. So we have to find special sequence for that. And this is especially constructed so that we have this theorem. So this is easy to prove once you have this. So this theorem says that in case Fn gamma converges to F, then if I consider a sequence Xn that converges to X, and Xn is an approximate minimizer of Fn, so approximate in the sense that I have a small threshold epsilon n which goes to 0. In case I have this, then this X is a minimizer of F, and also the value of the approximate minimum converge to the minimum of F. This is precisely what we want. So this is what I will want to prove. There is another thing. Gamma convergence says something when you have converging sequence, but it does not say that the sequence you will obtain will converge. So for that you need some coercivity argument. So in this case, since you have a sequence of functional, what you need is called equicoercivity. So it means that if you have a sequence which satisfies such an uniform bound, which normally we can prove, then the sequence Xn is compact, so it converges up to a subsequence. And this property is often quite difficult to prove. So you have to keep this in mind also. And so two other properties. So this one. So if you have Fn which gamma converges to F, you can add a continuous function and you preserve the gamma convergence. However, you cannot have Fn plus Gn. Gamma convergence is not stable upon addition because of the recovery sequence. And also, often intuitively we believe that gamma convergence is stronger than pointwise convergence. So pointwise convergence is Fn of x converges to f of x for fixed f. But it's not true. Gamma convergent is not neither stronger nor weaker than pointwise convergence. So this, if we want this, we have to prove it separately. Okay, so now let me come back to the perimeter. So there is a very classical, as has been already explained, very classical approximation of the perimeter which has several names. So Van der Waals, Canillard, and very often we call it Modica-Mortola because of this famous theorem. It is this one. So I have so in my computer box D, I have say a density U. So you can think of topology optimization in the sense of density optimization, for instance. So U means like a density, and this. So I need a double well potential W, and this gradient, and when epsilon goes to 0, essentially this potential will force U to be 0 or 1, and this gradient somehow counts sharp variations. And in fact, this is what is proved. So Modica-Mortola theorem. So it says that when epsilon goes to 0, this function gamma converges to this. So what is this? This is the relative perimeter of the set U equal to 1 if U takes value 0 or 1, and U is BV, and plus infinity otherwise up to some constant which is expressed like this. Okay, so this is a called gamma limit of this functional. So it's is very nice because this is what you need, the perimeter, in case U is a characteristic function of a set of finite perimeter. And otherwise, plus infinity, so it's also nice because it penalizes intermediate densities. So usually, you know, we want to optimize shapes, density, we have gray everywhere, but this will kill the gray. So it's nice. So this is what I say here. This is nice at first sight, but when you want to implement this, you have some problems. First of all, you cannot, in the functional, consider the characteristic function of a domain. Let me show you again. You have this. Of course, you must be H1. You cannot be 0 or 1. So in fact, you are obliged to incorporate intermediate densities. It's not a choice. So this might be seen as a drawback. Perhaps you want to apply directly shape optimization method. And another drawback is also because this gradient U square, if you want to optimize, so once you have epsilon fixed, you want to find a minimizer, an approximate minimizer. So usually we apply descent method. So the Fréchet derivative of this gradient U square will lead you to a Laplacian of U, and this is not very good in practice. So we can, to understand this, think in terms of a gradient flow in continuous time. And if you write this, then it's like an explicit Euler scheme. And so you have a CFL condition, and essentially you will have small time steps. So it does not behave well. So of course you can imagine of using an implicit scheme, which means that you replace somehow the Laplacian of U by the inverse of the Laplacian. But in fact this is quite related to what I will present, and why not to in fact incorporate directly the inverse Laplacian in the functional instead of dealing with the Laplacian itself. Okay, anyway, all these problems come from this gradient U. So let me, in case, show you again. The problem comes from this part. Okay, so how can we get rid of this? Well, to be honest, to have complete proofs of all what I will say, I will have to restrict myself to the case where this is really a box, so a Cartesian product of intervals in dimension 2 or 3. Okay, so the thing we do is the following. So I need a few notations. So this is a functional I'm introducing. So so I have omega, this domain. You have its characteristic function chi omega. And what is this? Epsilon, I will use it many times, so it's useful to keep this in mind. Epsilon is a solution of operator of this linear elliptic equation, so diffusion equation. So as I have said, it somehow here appears the inverse of the Laplacian somehow. So it's here is an implicit formulation. So this is not difficult to solve, of course. So this V epsilon, I call it, so it depends on U at the right hand side. So so you can define the solution operator L epsilon. This is of course linear. So I put it here, and this as notation I will use it many times. Is a L2 scalar product. So it is this. So I integrate this against the characteristic function of the complementary of omega in D. So it's very easy to understand in 1D. In 1D, here is what happens. So I take D, the interval -1, 1. I take omega 0, 1, so this one. So chi omega is the Heaviside step function. I apply this, so this is a diffusion equation, so we get this blue curve, and then I integrate against the characteristic function of the complementary of omega, which is this step function. So obviously when epsilon goes to 0, this becomes sharp, and when you integrate, the significant values will be concentrated around the jump. And in fact, what you obtain with direct calculation, so you can solve by hand this, and you calculate this, and at the limit you find 1/2. And in 1D, the perimeter of this omega is the number of jumps, since it's 1. So it's half of the perimeter. So this is what happens in 1D, and intuitively it happens the same in all dimensions. So indeed, so to be more precise, I introduce a kind of relaxation of the function in some sense. So in what I presented, I consider omega as I consider u as a characteristic function of omega, but you can replace by u function between 0 and 1 to be useful, to have a convex set here. So I recall you, so it was this was epsilon chi omega, and it was the chi of d minus omega, the complementary. So it replaces it by this, very natural. You can also, because epsilon is self-adjoint, because epsilon 1 is equal to 1, you have also this formulation. Okay, so I put tilde to say that it applies not only to characteristic function but also to any u in this form. What we prove is the following. So this, in fact, is exactly the same as the theorem of Modica-Mortola. So we have exactly the same properties. So it's okay. But what did we gain? In fact, several things. The first thing is that, as long as you will not see why it's so important, but I will use it a lot. You have a dual formulation of this functional, by you can calculate it by Legendre-Feld transform, so it's like dual formulation, an energy formulation. So you can write this like this, so all this like this. Okay, it will be useful. Another thing is, so you have no, of course it was the goal, you have no gradient u. Here you have gradient of v, but not of u. You have some weak star continuity property to have existence of minimizer for epsilon fixed. And what is important, and what is also new, is that you have pointwise convergence to the perimeter. So this is quite nice. It is there is a variant which is already known. It consists in, instead of using this elliptic diffusion, it consists in using the heat kernel. Some people have done that. These people, for instance. So more or less you have the same properties. One main difference is that when you use the heat kernel instead of this elliptic operator, you don't have this variational formulation, which I will use a lot. Okay, so now what do we do in practice? We want to minimize, in fact, something. So we have a cost function plus regularization by the perimeter. You replace this by the approximating functional, and in fact, you have at the beginning normally you have a cost function which is defined on the set of domains, but you have to extend it in some way to the set of function with value between 0 and 1. So you need some relaxation, interpolation, something like this. But the only thing you need in theory is that this is continuous. Because of gamma convergence, if you add a continuous function, you keep gamma convergence. Okay, so it's natural to do that. Equicoercivity, I told you it's important, so you can prove it. It's not at all easy, but you prove it with this functional that if you have this uniform bound, then you have convergence of your sequence of minimizers up to a subsequence. So in the end of all this, what you get is that if you take an approximate minimizer of this functional, then you have convergence to the infimum value of the target functional, and also you have convergence of up to a subsequence of the approximate minimizers to a minimizer of the target functional. Okay, so this is nice. Now, yes, I may add a small complement. Gamma convergence, in theory, addresses the convergence of global minimizers. And the problem is non-convex, so in practice we hardly find global minimizers, we don't know. So we find local minimizers, so what can we do about local minimizers? What we have been able to do is the following. We consider optimality conditions, so this approximate functional, you calculate the Fréchet derivative. It's very classical, you obtain this, and this, so this gradient of the approximate functional pointwise, so converges at point x, so on the boundary. So if I have box D, I have omega here, D, I take a point x at the boundary. So if I minimize this the approximate function, I will deal with I will get an optimality condition with this gradient, and this gradient converges at this point to the shape derivative of the two perimeters. So we are consistent also with derivatives, and it gives some information on first order optimality conditions.
You get this result for any u, or you have some smoothness on u?
You have some smoothness. U is chi omega.
Ah, okay.
Of course, because otherwise it tends to infinity. And omega is smooth here. Otherwise, I don't know how to write curvature. Okay. Now, in practice, again, you have so you want to minimize this. You replace this by the approximating functional, but you need a sequence of epsilon. Typically, you start with some epsilon max, which is big enough, and you divide by 2, for instance, at each time. For each epsilon, you minimize, say, completely, or you have some stopping criterion. And then you use it as a starting point for minimization with smaller epsilon. But there is one problem, is how to optimize at epsilon fixed. So we can do, roughly speaking, two things. Either you have the extension in the convex set because you know that, so you incorporate intermediate densities, but you know that they will be penalized in the end. So it makes a lot of sense to do that, and you have to minimize something like this. Or you minimize in the set of domains, and you apply shape optimization methods. You can do both. So in the first case, one question which arises is how to extend the cost function, which is at the beginning defined on domains. You have to extend to functions, to densities. So the natural way to do that is by relaxation, if you can. But it's not obliged to do that. It's natural. in the theory, it's not. You did not do that. I will give some examples later. And then once you have that, then you have a nonlinear programming problem to solve. So you can apply general method, or you can use the information, the variational formulation I showed you to write the minimization problem like this. And in case this is, for instance, linear in U, then you have interest to use an alternating method, because minimizing in V amounts, minimizing in V, it means in fact solving only the diffusion equation, so the L epsilon, so you need to do that. And solving in U, minimizing in U, if this is linear or easy, it can be straightforward to minimize. In case it's straightforward, the alternating method is good. For instance, okay, I will give some examples. Okay, and in the other case, you can use shape and topological derivatives if you want to keep domains. Okay, so let's consider a very simple example. So I have this cost function. This is a compliance for the conductivity. So notation is a bit unusual, but I use it for the density. So I use Y for the temperature. So it's a two-phase conductor. So conductivity gamma 0, gamma 1. So this is a conductivity equation with a boundary source, for instance. A nice thing is to write this cost function by the dual energy, which is this one. And what is known in the world of homogenization is that you can, if you relax in the sense of lower semi-continuous envelope for Wickster topologies, so what you need to have compactness also, is that the relaxed formulation is this, can be written like this. So I put everything there. So I put the approximate perimeter here, and here the conductivity, and here the volume term. And so you have three minimizations, and you can alternate. And what does it mean? Minimizing with respect to tau is just solving this. You cannot avoid to do that anyway. Minimizing in V is solving L epsilon, so you have to do that in the method. And minimizing in U here is decoupled in space, so it's very easy. You have an explicit formula, which is this one, and you obtain, for instance, in this benchmark problem, the optimal heater. So you have heat flow here, and here you have a fixed temperature. You obtain such results. So alpha, I recall alpha is the weight you put for the perimeter. So for alpha small, you obtain something like this. You increase alpha, so you want less perimeter. You obtain this kind of things. This is a weak phase. Okay, so it's nice, but elasticity is nicer. So we can do the same, but it's more complicated because, as you know, if you want to do the relaxation, the proper relaxation, you need to include here around 2 laminates, but it's known. So the relaxed formulation has this form, at least when we have a weak phase. And again, it's the same. Minimizing in V is L epsilon. Minimizing in sigma is solving the equilibrium equation. And minimizing in U is again explicit, spatially decoupled, so it's very easy. And you obtain this. So it's a classical cantilever. I increase alpha, so alpha small, and I increase. And you obtain these things. Just one comment, what you observe, and something maybe you don't like, is this thing, this artifact. This is due to the relative perimeter, because this is for free. You don't pay for this. So the method it's not the method. It's the functional does that. Okay. I will speak about that later. You can do the same for microstructures. So you want to minimize, for instance, here to minimize the Poisson ratio of macro cells, the RVE, representative volume element. Here I duplicated it just for vision. So in this case, you don't have an homogeneous formulation for this problem, which is itself a problem of homogenization, but I don't know how to find an homogeneous formulation for this, a relaxation for this. So we do something else. I cannot enter into details, but essentially it's like SIMP that we do. So we have so U is a density, think of that. U is a density. You apply, so like in SIMP, you apply a filter, and then you apply an interpolation profile to define so the elastic coefficients in intermediate materials. So can think like SIMP. So, but the difference is that we don't. We have mathematical arguments to find the interpolation profile, and also what we use is a level set formulation to write in fact densities as a characteristic function. So in the end, it's a level set method, but I cannot give details on this unless you have questions after. But this is not the thing I want to point. The perimeter, you observe the effect here. So here we have negative Poisson ratio. For those who are familiar with this, it's obvious. And if it's without perimeter penalization, and if you have you put perimeter penalization, you have this which has less perimeter. Poisson ratio is still negative, but less negative than this one. Short comment: we have periodic boundary conditions. So also in the perimeter, we include periodic boundary condition on the L epsilon and not Neumann. But I will give more details just now, because one variant is a total perimeter. So let's think to this example of the cantilever. You had this artifact near the external boundary, and in case you don't want that, you want to minimize the total perimeter. So you will want to count in the cost the part of the border on the boundary of the box. So the total perimeter, you can define it like this, and also you can prove these equalities. So it's the same kind of formulation, but you need a test function in d bar. And so you don't. It was so it's again the essential boundary, but it's not intersected in D. And the thing we do is that we only replace in L epsilon. This is L epsilon, but there was a Neumann boundary condition, and we replace it by this Robin boundary condition. So that's why we write L epsilon R for Robin. And if we do that, we can prove in fact this result, that this functional convergence. So for the gamma convergence and the pointwise convergence, so the same in fact the same thing as before, but for the total perimeter. So it's quite easy. You only change the boundary condition. So what we get for the classical cantilever again? So this is not with homogenization. It is with the SIMP type approach. This is with the relative perimeter, so you see the same kind of artifacts, and with the total perimeter, you see these things. Okay. So let me now turn to the multiphase case. So in the multiphase case, you have a partition of D in n phases, and typically an example of cost function is this one. So you have the sum of the perimeter of each phase, and you have a volumic term which is very simple, but I want to focus on this, so I take something very simple here, and I will say a few words on how one can perhaps change this. So you can, of course, write this like this, and in fact, if you can relax and replace this by a ui, and in fact, in the if you want to consider not only characteristic function of partitions, but function between with values between 0 and 1, the space, the metric space you want to consider is this one. So you have n functions between with values between 0 and 1, and you have a constraint that the sum at each point is equal to 1. Then we want to approximate this by this, it's natural. As I told you, we have a small problem, is that, or a big problem, in fact it's not big, is that Gamma-convergence is not stable upon addition, but here you can, because we have pointwise convergence. So because of pointwise convergence, we take as a recovery sequence in the lim sup inequality, we take a constant sequence, and now it's okay because you have sequences of function which satisfies the constraint sum is equal to 1. I mean, you take a sequence which satisfies you are in the space X, so you take it as a recovery sequence, and you are in X. So here it's fine. And in the end, we prove this. So because of gamma convergence, we have also equicoercivity, and in the end, you can replace this by this, and we get the convergence of, say, optimal solutions for the approximate problem. Okay, so then let's speak about algorithms. So for epsilon fixed, you have to solve this. So I use here the variational formulation for the perimeter functional. The thing we are a bit afraid is how to minimize with respect to u, because we have this constraint x, so sum equal to 1. And in fact here it's very easy, because in u the function is linear. So you want to find to minimize the linear function on the simplex. So you are on an extreme point. It's very easy. So you have to in fact if you write this zeta is the weight against u, you have this and this. You put all your value where this function is the most negative. So in the end, at each iteration, u is 0 or 1. So you have a partition at every iteration, even for epsilon fixed, not at the limit. So classical problem, the triple point. Here, what we do, we put some function gi to have so that it's to enforce somehow the phases red here, blue, and green here, and here the perimeter does the work to minimize. So you obtain this here for the quadruple point. Classical, you obtain this. These are theoretical solutions. And in image classification, maybe I skip this. So I want to present this in case you have a cost function instead of g in your cost. So you have this, and here you take a non-local functional like this. So with a like in image processing, a blurring kernel. And it's non-local, so if you want to apply alternating methods, you have a problem because the pixels are coupled, and so you don't know how to minimize exactly. And we can arrange with this by proximal gradient formulation, replacing this by this. With lambda is a very classical, so lambda is a Lipschitz constant of the operator you have. So in fact, again, the thing is that in the end you have nested minimizations, and in each direction it's explicit. So you solve epsilon, then this you do nothing, and this you have. Because of the proximal formulation, you have a projection. This is for the two-phase case, and in the multiphase, you have a projection on a simplex. So these are examples you can get. So you know the blurring kernel, and so you minimize the function with perimeter penetration for each phase. I would like to say something about this problem of what I call interface energies. Is that here so we have the same type of objective function plus not perimeters but say areas of interfaces. So the interface between omega I and omega j, I call it like this, and I have some weights. And what we do, what is easy to see, and it's known that say in 2D the length of this interface is equal to the perimeter of this plus the perimeter of this minus the perimeter of the union of the two, so this divided by 2. This is true, and if you replace this by the approximate perimeter, in the end you get this, and you have a pointwise approximation. But what about the gamma convergence? We have some trouble because we have minus, so no way gamma convergence has some problem with addition already, but with minus sign it is much worse. So there is something to consider. So the first thing is, in order to have gamma convergence, you need to have some semi-continuity. This is a necessary condition. It's known that the coefficients, which are in some context called surface tensions, must satisfy a triangle inequality, which says that somehow if you have two phases here, you have no interest to put something in between. If you don't fulfill this, if you have interest to put, for instance, blue between green and red, then this layer can be arbitrarily small. And this means that you lack lower semi-continuity. So to avoid this, it's natural, and it is true, it's known that you have to impose this constraint. Then you have lower semi-continuity. Then to approximate in the sense of gamma convergence, maybe I skip the details, but you have some algebraic properties which relate, as I told you, for two phases, length of interfaces in terms of perimeters of domains, but you have, it's useful to gather some phases. So you have some union of domains. Where did I write this? Omega S is here, union. So you arrange so that these, if you can, these this weighted sum of length of interfaces can be written as a weighted sum of perimeters. You can do that if you have an algebraic condition, which can be written as a matrix problem. And in this, but in order to have gamma convergence, you need to have this coefficient positive. So it's a question of conical combination. So the thing is that if you want to be able to reformulate this interface energy in terms of some positive sum of perimeters, you need such positive coefficients, and you have conditions for that. In fact, if this is possible, the triangular inequality is automatically satisfied, so this is in one sense. And in the reverse sense, you know that up to 4 phases, if you have the triangular inequality, then you can find a positive reformulation with positive coefficients. But for n greater than 5, it's quite strange. We have counterexamples. Okay. Then, in order to apply algorithms, one thing which is interesting is the convexity of the functional. So the approximate function at epsilon fixed. We want to have, we need some convexity properties in order to apply a dual formulation. So since we deal with function with sum equal to 1 in the space X we consider, the associated linear space is this one, sum equal to 0, and we need the matrix of surface tensions, which we call Q. We need it to be what people call conditionally negative semi-definite. So it's like negative semi-definite, but on this linear space. And if you have this algebraic property, then you can prove that the function, so the function with the approximate interface energy is concave, which leads you to consider a dual formulation by Legendre dual formulation, which can be written like this. So the interface energy can be written like this. So it's a variational formulation for for several phases. And with this, you can apply alternating minimizations. And it's explicit, it's linear in U. That's the point. So again, it's easy. Okay, just one or two examples. This is the same problem we have with the quadruple point problem. So here I force this phase, this phase, this phase, and here I want to minimize interface energy. So here I take all the weights equal to 1, and here I change so that I penalize more between blue and red, and between white and green than between these phases, so that in fact you obtain this in the end, just to see what happens. I will skip this technical thing, but just to show you results. In case you have volume constraints on the phases, you can apply an algorithm which is quite efficient. Anyway, you obtain such results. So here I minimize the interface energy, and I want the volume of each phase not to change during the iterations. So this is what you obtain with the surface tensions all equal to 1. And here I say that between anterior phases and the white phase, it's less. Well, this is initialization, it's equal to 1, and if it's less between, say, this phase and the exterior, then the phases go to the corners because of the fact we have relative perimeter. In case you do the contrary, you penalize more between, for instance, this phase and the exterior phase. The phases want to be together, so you obtain these kind of things. Except, and in fact, if you think this is only local minimizer, because in fact the global minimizer will want to put everything at the boundary because it's a relative perimeter, so you pay less. And in fact, it is due to the epsilon max. So when you decrease the epsilon, when you have epsilon large, when you start, you see far away. So this wants to go to the corner, unless if you have epsilon small from the beginning, this does not see the boundary. because the diffusion equation you have only local effects. And you have same kind of thing with 5 phases. Here one is fixed, and this I have 3 phases. So usually people say that these are liquid phases, this is a vapor phases, this is solid phase. And typically what happens in practice is that normally liquids like water have better affinity to solid than to air. And this is why we have capillarity effect. So, for instance, this one prefers to be near the wall than near the air. So you obtain this in this case, and this in case in between the phases you change the penalty between liquid and liquid is less. So so liquid want to maximize to have longer interface. So you have this, which is in fact again a local minimizer in this case, because here I have a relative. So this is for free. So if you have epsilon big, in fact everything is at the top, but it's an effect of the fact we have relative parameters, an effect of modeling. Thank you.
Thank you very much. Other questions, comments?
In painting examples,
Yeah.
you need to tune epsilon carefully to get the picture you want. Do you have to tune parameters, or
You mean the weights, these weights?
yes? Do you need to tune them, or you just
They are given, they are fixed from the beginning. Here I fix equal to 1, and here I change. It's on purpose I would like to penalize more, so I put 2. I cannot put more than 2 because of the single inequality. So I put 2 between this phase and this phase, for instance.
so these 2 pictures, the outputs are from 2 different parameters.
Yeah, yeah, sure.
All right. If you change the square slightly, if you perturb the area you cover slightly, do you have similar results?
If I perturb, what?
If you perturb the dark area slightly, a small deformation of that,
No, because
do you have similar results?
yes, we have, because in the result I showed before, it was a circle.
Square. You don't keep it as a square. You just deform the square slightly to make.
I did not try, but I think it does not change.
Have you tried?
No, you not. But what I tried, for instance, I showed before. It was a disk. It was the same with a disk.
For example, the edges become slightly
With this,
curved. Also, can you change the disk slightly to make it not?
I use the disk. I use the square, but nothing in between. But I can do.
I mean, whether you have any stability of such schemes, that means if it's not an exact round disk, rather than a slightly deformed disk, whether you get something similar.
I think it will change nothing, but I did not try.
Have you?
I did not try.
Okay, that's fine.
So concerning the numerical implementation, we use spectral code, so fast Fourier and
Yeah.
grid size and epsilon. So what is your experience
Well,
of perimeter approximation?
yeah, it depends on the context. If we in this example, like related to image processing or partition, where you don't have elasticity equations behind, I use FFT. So in fact, the Laplacian is discretized with finite differences, and I solve in a Cartesian grid, and I solve by FFT.
And grid size and epsilon, so
Yeah, that's another question. So, of course, usually the epsilon max, it depends on the problem, but I start with big, typically the size of the full box, and I decrease until the size of the grid. It does not make sense to take it smaller.
So this is somewhere between a question and a remark. You mentioned this open problem with arbitrary surface tensions which satisfy the triangle inequality. That was not gamma convergence was not clear.
Yeah.
So in this work which you mentioned, where instead of using the resolvent kernel, you use the heat kernel,
Yeah.
which morally speaking is not very different.
Yeah.
I mean, the heat resolvent kernel is like discretized heat kernel. There you get exactly the gamma convergence in this general setting without kind of the constraint of having less than 4 or less than 5 phases. So I was wondering why you couldn't adapt that proof to your situation.
But you need lower semi-continuity, so you need the triangle inequality.
Yeah, triangle inequality, but just the
Yeah.
triangle inequality. Not the, you had this, I mean, you were phrasing it as a question,
Yeah.
and then you had the statement that you had an additional condition which was always satisfied for 4 phases or less. And in the case when you have the heat kernel, that's not needed.
Okay.
It's in this, is it?
Yeah, I know what you say. I have been fast in this something.
But
Yeah.
you had this,
Equicoercivity. Yeah. In case, wait, yes, because I know how to prove it when we have formulation in terms of perimeter with positive coefficients.
yeah.
This just because I know how to do it like this.
Yeah, but I'm just saying that in principle there should be the ingredients for proving this your result in the general case because it works for the heat kernel,
Yeah.
and I don't see why it should be so different when you use the.
It should be the same, yes. So it's very interesting because it's a bit of problematic to have this restriction.
Yeah, at the beginning you said that you had a kind of a restriction to compute your approximation of the perimeter on the rectangles. Why is it so? I don't see.
It's a technical aspect. It's to prove the gamma convergence in the proof of the gamma convergence. We need in the inequality. Let me think. It's a technical thing.
Okay, maybe we can.
Yeah, it's something because we need. At some point, we have an estimate, and it helps to extend the domain by symmetry and periodicity.
And if I may, you motivated also at the beginning of your talk this introduction of this approximation of the perimeter by the fact that you cannot compute the topological grid. So can you compute it here?
Of course, yeah. I have results on that, but
Did you use it, or
I use that also for microstructure for many things. But I did not show that because I have to choose. But in fact, this problem, for instance, this behind it's a topological derivative. There is some business, the algorithmic thing. In the end, it's like simp, but we obtain the same by using topological derivative.
And let's think.